Okay, good morning, everyone. So we'll continue with where we left yesterday on the continuous time Koopman. So just to quickly recap, not the entire thing, but just starting from the continuous time system. So we start with the continuous time system, x dot equal f of x. Assume that the solution or the flow of this is given by phi t of x. And then in contrast to the discrete time, for the continuous time, we have a family of Koopman operator, right? And this family is basically parameterized by the time t, and we denote it by this kappa t. So kappa t is the family of Koopman operator, and the action of this on any function f is given by f phi t of x, where phi t is the flow, right? And this definition is kind of consistent with what we did for the discrete time. If you make t equal to 1, right? So just one time step back. So since the continuous time system has a little more structure now, apart from the operator itself or apart from the family of operator, one can also talk about the generator for this operator, right? And how this generator is defined. Generator is defined with the following definition: limit t goes to 0, kappa t minus identity, acting on any function psi. Psi could be any function divided by t, and that is given by, it can be shown that this is equal to f of x dot gradient of psi. I can write it either like this using the gradient notation, or I can write it using this the standard notation. And we also saw that this is nothing but the Lie derivatives. Those who are familiar with differential geometry concept, it is nothing but the Lie derivatives of the function psi along the direction of vector field f. Okay, and I mean, I'm not doing the proof of this. You can see that I can point to the reference for the proof of this, but basically it's also very intuitive, because what you're doing here is you're looking at the change in the function psi, how the function psi is changing in the infinitesimal sense when you look the change along the flow of the system x dot equal f of x, right? So that is precisely what this is, right? So that is also comes from the Lie derivatives, but without sort of referring to the Lie derivatives, there is alternate proof of all these things, and I can point you to the paper, or I can point to the book. Personally, I feel that this is like a fantastic book to, if you want to start with this density-based approach for dynamical system. The name of the book is little deceiving, but I think it's like a very good book, because it doesn't really go into it does the right balance of talking about some of this very abstract concept, especially when it comes to function spaces, measure theory, and so on and so forth, which is sort of the necessary ingredient or the preliminaries that are needed to understand the linear operator theory. I mean, as you have seen, I haven't really done any of that, right? And I hope you guys haven't missed that, right? But once you start proving certain things, once you want to use this concept in a paper and so on, you need to be familiar with some of those mathematical jargon. Okay, so the name of the book from where you can actually look at where you can actually get a more detailed introduction to many of these things which I've talked yesterday is called as the authors is L07 and McKay. The name of the book is Chaos, Fractal, and Noise, Stochastic Aspects of Deterministic Dynamical System. Let me make sure that I'm not sort of quoting the wrong book. Stochastic aspects of not deterministic, stochastic aspects of just the dynamics, okay, not deterministic, because the book also has something to do with stochastic. So chaos, fractal, and noise, stochastic aspects of dynamics, okay. And the authors are, L07 is the first author, the second author is M-A-C-K-A-Y, not M-C-K-A-Y. M-A-C-K-E-Y, okay. It's a very good book, at least the first 2 or 3 chapters. I mean, the later on chapter actually goes a little deeper into all these things, which may or may not be necessary. But the first 2 chapters are actually good chapter. Okay? Of course, there is now like explosion in terms of papers on the use of Koopman and the Perron-Frobenius theory when it comes to all sorts of things, right? Application, theory, and so on and so forth. But that's actually fairly recent, I would say. It's not more than 10, 15, 20 years old, right? I mean, especially it become more popular. People have been working on this for quite some time, but it's becoming more and more popular given the data focus of it. This book doesn't have the data focus because this book is fairly old book, right? It's I don't know the exact date, but I think it's certainly more than 25 years old. So the data aspect is not there in this book. But anyway, it's a good book to sort of start with motivation, which is what I gave in a previous lecture. Why do you want to look at systems from a density perspective? What are the how these operators are defined, and so on and so forth. Okay. So with that, let me get back to this continuous time Koopman operator. So let's look at some example, just like we look at example in the discrete time case. So we can again look at this example in the continuous time case. By this time, you should be expert in this the way I'm constructing the example. So let me construct this simple example, which is x1 dot equals x1, x2 dot equals x2 plus x1 square, right? So now this is a nonlinear system. It's a finite dimensional nonlinear system, and then we want to understand how this the Koopman. So we won't construct the Koopman family here, but we'll just directly construct the generator. So I'll tell you how the generator of this operator looks like, because that's much more natural given that it's a continuous time system. So again, we actually come up with the choice of the basis functions, and as you can see, the basis functions in this case is kind of obvious. So we'll use x1, x2, and x1 square. So this is my basis functions, okay? And now, with this basis functions, I could do psi dot, okay? So what is psi dot? Psi dot will be nothing but x1 dot, x2 dot, and x1 square dot, okay? If this notation is not too confusing. So what I'm doing is I'm just taking the time derivatives of each of these functions. X1 square dot, okay? Now what is x1 dot? X1 dot is nothing but x1, right? Let me just call this as psi1, psi2, and psi3, okay? So x1 dot is just x1. What is x2 dot? X2 dot is x2 plus x1 square. What is x1 dot square? It will be 2 times x1 dot, which is 2 times x1 square, right? Now what is this? This is nothing but psi1. This is psi2 plus psi3, and this is 2 times psi3, right? So I can write it in the matrix form as 1 0 0, 0 1 1, and then 0 0 2, right? Times psi. Okay? So now you have a finite dimensional Koopman generator for the system, okay? Because we have what we have is basically we have psi dot equals I don't know what's the notation I'm using. So let's introduce some notations. Let me see what notation I'm using. Yeah. So I'm using the notation. Okay, let's just use this notation, which is sort of also the notation for the Lie derivative. So I'm using the notation of LF for the generator of the Koopman operator. Okay. So LF. So the subscript F here signifies that this is the generator for the vector field F, and LF is the notation for that. So what we have is and your LF now is the finite dimensional matrix given by 0 0 1 1 0 0 2. Okay. Things may not be as nice for this example. As I said, I mean, there is sort of a marriage of two here because there's a dynamical system as well as a choice of basis. So this for this particular example, both these things actually work together to give you a finite Koopman, but that will not necessarily, that may not be the case all the time. For example, if I just make a small change in the system, let's say, so let me just call this as example 2. If I just make a small change in the system, so x1 dot equals x1 plus x2. So what I did is actually I added this x2 term, and I keep the second at the same. So x2 plus x1 square. Okay. Now you see the system, I mean the same basis may not work, right? Because now you choose the same basis, let's say x1, x2, x1 square, which is again we call it as psi1, psi2 and psi3. So if you do the thing again, what you get is that you get yeah, so you get, I'm just going to do this, I'm going to just skip some steps here, right, as long as you follow me. If not, then you can ask me. So I can just do psi1 dot equals, what is psi1 dot? So psi1 dot is x1 dot, which is x1 plus x2, which is psi1 plus psi2, right? What is psi2 dot? Psi2 dot is nothing but x2 dot, which is x2 plus x1 square, which is psi2 plus x1 square is nothing but psi3, which is psi3, right? Now, what happens to the psi3 dot? Psi3 dot is nothing but 2x1, x1 dot, which is 2x1, x1 dot, which is x1 plus x2, which is 2x1 square plus 2x1 x2. See, now this is a problematic term. Well, so I can write this as 2 times psi3 plus 2 times x1 x2. See, so this x1 x2 is no longer in my basis functions. So you get terms which are not in basis. What it means is that the action of the Koopman on these bases is not closed, right? Because you're getting some terms which are cannot be. Now you can say I could introduce one more basis function x1 x2 and keep on doing this, but if you do put x1 x2 as a new basis, let's say psi4, when you do the psi4 dot, you will get some terms which again you'll have to increase the basis, expand the basis function. So this for this system, I don't know the choice of basis under which the action will be closed. So this will lead to a this will not lead to a finite dimensional Koopman. All you can hope is that actually to get a projection of the infinite dimensional Koopman on this finite dimensional basis, which are spanned by whatever basis functions you have. Make sense? Yes. Yes. Yes, your observation is absolutely right. Is that for the system you have one equilibrium, and for which you can actually find a close. But I will hesitate to sort of make that statement in general. That I mean, if could be right. I mean, there are some papers which have actually pointed to that. So if I understand what he's saying is he's making the following statement. Let's say I start with a system, finite dimensional nonlinear system, which has 2 limit points, right? The limit omega limit set, or in this case, this is a 2 stable equilibrium point. You will never able to find any basis under which the action of Koopman will be closed. That means there is no finite dimensional Koopman. Is that basically sort of paraphrasing what you're saying? So, which is true. There is a paper, I think, which kind of points to that. I haven't read that paper in detail, just based on the title is what I'm saying, and that's exactly what the title is saying, that if you have a system which has multiple equilibrium points, then you can never have a finite dimensional immersion. Okay? So this is basically you're trying to immerse the nonlinear system into a finite dimensional linear system. So all you can get is actually the is a truncation, okay? Based on that. And things could even be worse than that. So even if you have a I mean, even if you have a system has only one stable equilibrium point, you may not able to find the basis under which it's closed. Although it may exist, it may not be easy to find. Okay? But certainly, if there are multiple steady states, then there doesn't exist. So don't even try on finding it. Make sense? Yes, good. So that's what I'm going to get to that. So what is the connection? So between this Koopman operator or finite dimensional Koopman operator and the system. So linearization based on the Koopman versus linearization based in the traditional sense at the equilibrium point. So how these two are sort of connected, right? And I will tell you once I'm done with this, I'll talk about connecting this the eigenfunction of the Koopman to this Hartman Grobman theorem, which is basically one of the main results when it comes to linearization of a system at the equilibrium point. Feedback, I mean, there is no control here. Yes. So here we are not actually doing change of coordinates. This is actually immersion, right? So in this, for this system, the original system was actually two-dimensional. What we ended up with the Koopman is a three-dimensional. So there is no change of coordinates here. So we're sort of special case, yes. So that's what I'm saying. So that has connection with the Hartman Grobman, which may or may not be of interest, but I think the eigenfunctions is actually a connecting link. Okay, eigenfunctions is actually could be used as a change of coordinates. Okay, so we'll talk about that, and that connects with the Hartman group. Okay. Any questions? So let's now actually talk about this, the dual of this, which is the Perron-Frobenius. So what is this Perron-Frobenius operator? So Perron-Frobenius operators actually propagate densities, right? So and as I was saying, I mean this Koopman actually takes functions and map it to functions, and it is defined in the way we defined it. But there is no sort of physical. I mean, something which may be physical for you may not be physical for me. So I'm sort of using that word very cautiously. As far as I see, it's sort of more abstract operator. Okay, but this Perron-Frobenius is actually much more physical. Like what I mean by physical in the following sense, right? So I gave that example to you. So imagine that you have some mass, right, or like some distribution of initial condition, which can be described using some function, and you want to know how this distribution of initial condition, which is described using function, will propagate forward in time, right? So that forward propagation of this initial distribution of point, which is mathematically speaking, can be expressed in terms of the initial distribution of point, you can characterize in terms of probability density function. So you have some initial probability density function, you want to know how that probability density function evolves forward in time. And that evolution is basically given by a Perron-Frobenius operator. Okay? So let's say if I have a discrete time system, xt plus 1 equals f of xt, and let's say you have some initial density rho of x. So this is purely deterministic. Right? There is no stochastics in this system. You have some initial density function rho of x. So it's a L1 function. If it is a probability density, then it's all positive, but it doesn't have to be positive. It makes sense, physical sense, when rho is positive because it's a probability density function. It integrates to 1 and so on. Now you want to know at t equal to 0, you have this probability density function. What will be the probability density function in a one-time step? Okay, so this function will evolve and give me a new function rho 1 of x. So what is this rho 1 of x in terms of rho of x? So what is the connection between rho 1 of x and rho of x? Okay, and that connection is given by this so-called Perron-Frobenius operator. So what does this Perron-Frobenius operator looks like? So this Perron-Frobenius operator can be defined more generally. I'm going to define it in a little more constructive, little more restrictive way. I'm going to define it under the assumption that this mapping f, so this f, what I'm using, I think I was using t, right, not f, sorry. So let's just use the t. This is mapping t, which is from x to x, is assumed to be invertible. So we assume that the mapping t is invertible. Okay, this mapping T is invertible. That means there is a unique inverse, right? So if you want to go back, there will be unique inverse. It doesn't have to be. I'll tell you how to sort of define this in the case when it is not invertible. But when it is invertible, you can actually define this Perron-Frobenius on a space of functions, on a space of probability density functions. So the notation we're going to use is this calligraphic P rho, P acting on rho, its value at x is given by, so this is a new function now, this is like a rho 1 of x, right, is given by, take the rho, the old density function, and do T inverse of x, okay, and take the determinant of the T in this. So this is the notation for the determinant. dt dx inverse, or I mean it's the same thing, but okay. So this where stands for determinant. Okay, so this is the definition. I mean, I'm calling it definition because I'm not doing the proof, right? So one can show that this is how this rho 1 of x will look like. That is a probability density function in next time step, and you can see, look at this proof of this in the reference I just gave you. It's okay. So this is under the assumption that T is invertible. Of course, you can define this even when T is not invertible. Like for example, we did the example of a logistic map. Logistic map is not invertible, but still you can define this Perron-Frobenius operator. Okay, so you see, the reason I'm saying that it is sort of very complicated to define is because now it involves T inverse. It also involves determinant, but it is actually physical because this is telling you something that you are kind of familiar with, right? Which is, okay, I have an initial density function. What the density function looks like in one time step. So this is how the density function, the new density function, will look like. This is in contrast to the Koopman, which is easy to write down, but it's not physical. Okay? Now, of course, this rho 1 here, you are more familiar with rho as a probability density function, but rho here doesn't have to be a probability density function. All you need for the rho is that it should be an L1 function. That means it's an integrable function. Okay, that's all. It could be positive, negative. So this definition is more general. Of course, we are more familiar with it when it comes to the when the rho has a physical interpretation of the probability density. Okay, now. You can, as I said, you can define this more generally for those who know a little bit about measure theory. I don't expect you to know about measure theory, but if this T is not invertible, then this Perron-Frobenius operator could be defined more generally on a space of measures, and there you don't need invertibility. Okay, just sort of for the sake of completeness, on the space of measures, this mu is a measure, A is a set. On the space of measure, this could be defined as, the reason I'll tell you why I'm writing this, although this, you may not, many of you will be familiar with this, but you see what is happening now. On a space of measure, look at this operator. And then sort of try to connect it with the Koopman operator. So let me just write down the Koopman operator in conjunction with this of x is f T of x. You see? So on the space of measures, this looks like it's exactly, instead of going forward, you're going backward. Right? So this is we wrote it as T composed with x, but here is mu composed with T inverse of x. So just like a 2 minutes description of what a measures are, right? So measures, what is a function? Function basically scalar value function in this. This is basically gives you, given a point x, this function gives you the number at a point x. Right? You can associate a scalar, one complex number or a real number, depending upon the function is from the mapping from to a complex plane or real plane to real line. Right? What are the measures? Measures are acting on the sets. Okay, so given a set, they will give a real number, and because the measures usually mostly you work with positive measures, which is you get a number which is a positive number. Okay? So the underlying space on which the measures act is the space of sets, which is the Borel space. Okay, and what you get is actually a number. Like the famous, or not famous, I mean the most common example of a measure space will be the Lebesgue measure, right? So which is like, if you are a real line, if you take any interval, the Lebesgue measure of the interval is the length of the interval, right? Now, if you are in a two-dimensional plane, if I give you any set, the Lebesgue measure of the set will be the area of that set, right? If you are in a three-dimensional space, if I give you any volume, the Lebesgue measure of the, if I give you a set in the three-dimensional space, the Lebesgue measure of that set will be the volume of the set, right? So that's the example of a Lebesgue measure. Of course, that Lebesgue measure is one example. I mean, you can construct various different measures, right? And that's the measure space, right? So on the space of measures, the Perron-Frobenius looks, I mean, I like to call it little simpler. All you have to do is basically take the mu composed. So the mu is your old measure. The new measure is given by mu composed with T inverse. That's your new measure. Okay. Now, what is the T inverse here? If T is not invertible, what do you mean by T inverse? T inverse basically means, what is T inverse of A? What is the T inverse of A? T inverse of A is defined as set of all point x such that T of x belongs to A. Okay. So this is how the inverse is defined when T is not invertible. So for this, you don't need to know, T doesn't have to be invertible, right, with this definition, because it's defined in the set theoretic sense. Okay. It is not defined in a pointwise sense. So, and that's why when T is invertible, you can now define the action of the Perron-Frobenius on functions. But when T is not invertible, then you define the action of the Perron-Frobenius on the measures, which are set valued function. Okay? And of course, there's a connection between the functions and the measures. If you know about this Redon-Nikodym theorem, which says that for any measure, I can actually define we can define a function using a Redon-Nikodym derivative, right? So I don't want to get there because I'm not going to use any of this stuff, but for those who would be interested, they can read more on that from that book. Okay. So anyway, so this is how the Perron-Frobenius looks like, and now you can see that this Perron-Frobenius is also a linear operator. Okay, it's very easy to check that, right? How do you check this? That okay, now I have P acting on a rho 1 plus alpha rho 2 of x. This will be equal to P rho 1 plus alpha P rho 2 of x. Okay, this follows from the definition. So it is also linear operator. Okay? So both these family of operators, Koopman and the Perron-Frobenius, are linear operators. Okay, and these two actually have they enjoy a duality property. So what do you mean by dual? So dual is now here defined in the function space, right? As I said, I'm not very precise in terms of defining these underlying function spaces, because I think when I talk about duality, I have to be more precise what I mean by like in what space these are actually dual. So if like there are various different ways of doing it. So the one of the standard way of doing it is actually when you're defining this duality, you define the Koopman. Now this is where I think the functional analysis is. Like if you have background in functional analysis, that will come in handy. So if you have to define the Koopman operator from the space of L infinity functions to L infinity functions, and define the Perron-Frobenius from L1 to L1. So now there's L1 and L infinity are actually dual to each other, and that's where this you can prove this dual. So leaving that aside, so if I just work in Hilbert spaces, which is all L2 spaces, then this is also true, provided it sort of confines the underlying space on which this is operating. But leaving that aside, so what do you mean by duality? So this is what I mean by duality. So if I look at the action of kappa on, let's say, any function g of x, okay, and then take f of x dx, okay, so this I can write in the inner product form as kappa g inner product with f, okay. This is same as g p of f, okay. As I said, I'm sort of very loose with this, or maybe if I just like, yeah, so we could just do this in the L2 space, okay, the big L2, if you want. So then we have to define this kappa from L2 to L2, and this p from L2 to L2, okay. And then, so, and this can be proved rigorously, right? So how do you show this? It's like one-line proof. The one-line proof is easier if you actually just, I mean, this proof is easier if you define this on the space of, for the Koopman space of continuous functions, and the Perron-Forbinian space of measures. Here you have to do some change of variables. So what is this? By definition, kappa g of x, f of x dx is nothing but g t of x, f of x dx, right? Now you do a change of variables now. So define t of x to be equal to y, assuming this is invertible. Then what it means that x equals t inverse of y, right? Now you substitute it there. So what do you get? So this g t of x, f of x dx is nothing but g of y, f of t inverse of y, okay. And now this dx, because of the change of variables, the dx becomes equal to dt, determinant of dt inverse of y, dy, okay. So okay, so this outer line is not for the modulus, these are for the determinant, okay, which is the notation we introduced. Now this is exactly the definition of the Koopman, sorry, the Perron-Forbinian. So this is g of y p f of y dy, which is g p of f, okay. So these are this is where the duality comes. Okay. Now, just like we have a, I'm sort of going a little faster because I think this is, but stop me if you have any questions, okay? Now, if just like we define the Koopman for continuous time, we can also define the Koopman for the Perron-Forbinian for continuous time. And just like we have a generator for the Koopman in continuous time, we'll also have a generator for the Perron-Forbinian in continuous time, okay? So just like we had one family of Koopman in the continuous time, similarly we'll have the family of Perron-Forbinian in continuous time, where this family will come from the will be parameterized by the time, and then we can use that family to define the generator for the Perron-Forbinian. Okay? And the generator for Perron-Forbinian will look very familiar. Okay? That's exactly the advection operator, okay, which is sort of the deterministic version of the Fokker-Planck. Okay. So let's see in the continuous time. So I'm just going to for continuous time, we have x dot equals f of x. Again, we have this flow phi t of x, right? The solution, right? And then we can now define p superscript t, rho of x will be rho phi minus t of x, and then this will be determinant of phi minus t of x dx. Okay. Now we can define the generator for this. So now this is like a one parameter family. Of I'm going to just write this as a PF instead of Perron-Frobenius, PF for short, Perron-Frobenius operator. Okay. Now we can again define the generator for this, which is limit t goes to 0, pt minus identity rho of x divided by t, and that is nothing but equal to minus of gradient of f acting on rho. Okay, and this can again be shown and this can be shown using even like multiple different ways. One of the way you can show is actually using duality. Now, I don't know if you're, I mean, some of you may be familiar with this. This is exactly the advection operator, or this is the advection sort of PDE, and this is a deterministic part of the stochastic, so if like a deterministic part of the Fokker-Planck equation, okay. Fokker-Planck PDE, which is used for propagation of the probability density function for a system with noise. Okay. Now, just like we define the Koopman PDE, one can also define a Perron-Frobenius PDE. So what is that? So that will be, let's say, rho partial t xt equals to minus gradient of f dot rho. Okay. So I hope you are familiar with this notation, right? So this is the what do you call it? This is a divergence operator, right? So the f rho is a vector, and then you are taking the dimension. So if I want to sort of open this thing up, this is nothing but if there are n variables, this will be partial xi, I equals 1 to n, fi of rho, okay, where f is the vector of n components. Okay. Okay. So what it basically says that, okay, if you have some initial density at time t equal to 0 as rho 0 of xt, that is at t equal to 0, then rho of xt at time t will evolve according to this PDE, and then from the Koopman theory, we know that this will be given by phi minus t of x, determinant of phi minus t of x dx. So this is the solution which is expressed in terms of the Perron-Frobenius generator or Perron-Frobenius operator. Okay. So that's the solution. Any questions? Yeah. Flow is not unique, then you cannot do it, say, in continuous time. You can still do in a discrete time, where like one of the cases will be like when you don't have the unique inverse, right? So you can still define the Perron-Frobenius even if it is not inverted, but you have to define it more generally on a space of measures. But in the continuous time, when you write down differential equation, we are assuming that the differential equation sort of has a solution and it's unique and so on. So that's why all this thing follows. Yes. Okay. So both the Koopman operator and a Perron-Frobenius operator, they themselves doesn't need any like invertibility assumption. But if you have those, then you get more structure. Okay. Any other question? So we should maybe introduce some notation. I don't know what's the notation we should use. I wanted to introduce some notation. So we use L for the Koopman generator. So maybe once it comes to that, maybe we could introduce some notation. Use LF. I don't know what notation I'm using. Yeah. Okay. That's not important at this point. Anyway, so now let me sort of try to connect this to, and this is sort of what I'm going to talk about now is sort of not even much popular in the Koopman community. I mean, there are some papers on this, including me and some few other researchers. And there is a paper, I can point to a paper which talks about this. Like this kind of questions we had in the beginning is how do I connect the Koopman to the state space dynamics? Because what we are doing is basically we said that, oh, this state space picture is way too complicated, right? Because if the system is nonlinear, the evolution of single point is way too complicated. Let me sort of try to move in the space of functions. Because in the space of functions, things become much more regular, and then I can actually describe things linearly, right? But when you do this thing, I think some things have to get lost, right? Because when you're describing system in the space of functions, you actually lose the information about this pointwise behavior, okay? Because you are dealing with functions. So pointwise behavior is more like if you think in terms of space of function, these are actually sort of a very small set. They're a very thin set, or to be mathematically precise, these are actually measure zero sets. So you lose information about what is happening on the measure zero set. But still, you would like to know, okay, if I do certain things on this space of measures, what can I say about the system in the original state space, right? Because ultimately, let's say if you're dealing with controller design and so on and so forth, I have to design controllers in the state space, right? I don't want to stay in the measure space. So measure space is a good space to maybe do design, but eventually whatever I do design, end up designing in the space of functions, I have to go back and implement it in the state space, right? So in that sense too, it is sort of very natural to ask, okay, what does it, like how does what I'm studying actually relates in the to the space of in the original state space, right? So and we can actually relate this using so-called the principal eigenfunctions, okay? So let me now talk about what is called as the principal eigenfunctions. And I've been, okay? So we're now going to put a little more structure to this. So let's say if I have x not equal to f of x, I'm going dealing with continuous time system, right? And then you do a linearization. So let's say I actually split the system into a linear part and nonlinear part, which you can always do without loss of generality, right? What I mean by that is I can write down this as ax plus some fn of x, right? What is fn of x? Fn of x is the nonlinear part, and what is a of x? A of x is the linearization. So you're basically what you're doing is you're writing this as ax plus f of x minus ax, right? And what is a? And then call this as your fn of x, right? And what is a? A is nothing but partial f, partial x at 0, assuming that 0 is the equilibrium point. So you are linearizing the system at the equilibrium point and then splitting the nonlinear system into linear part and the nonlinear part, okay? And right? Now I can write down a Koopman generator for this, and I can ask, and I will try to find the eigenfunction for this, right? So now I'm sort of exploiting the structure a little bit, okay? So what is the equation for the eigenfunction? So if I want to find the eigenfunction with the eigenvalue lambda, phi lambda of x, right? Then this should satisfy phi lambda of partial this times f of x should be equal to lambda phi lambda of x, right? So that's the definition of the eigenfunction associated with eigenvalue lambda. I mean, if I write down this, I think I never maybe wrote it down, so I can write it down. So if I write this in terms of the generator, right? So phi lambda of x, right, in terms of the operator, then this will behave like lambda t phi lambda of x. Okay, this is kind of go hand in hand. Now, it can be shown that right, that the eigenvalues of linearization of a nonlinear system will also form the eigenvalues of the Koopman operator, as we discussed yesterday, right? So if the linearization will have n eigenvalues, then all the eigenvalues will also form the eigenvalues of the Koopman operator. Now you can ask the question, okay, what are the corresponding eigenfunctions? Okay, so the eigenfunction, let's say lambda is the eigenvalue of the linearization. Okay, so lambda is the one of the eigenvalues of the linearization. Eigenvalue of A. Okay, I just use lambda instead of I because I think whatever I do will sort of apply to all the eigenvalues. Lambda is the eigenvalue of A. Now, what will be the phi lambda of x? Okay, what will be the phi lambda of x? That is the corresponding eigenfunction with this eigenvalue. Okay. Now, the system has a decomposition which is a linear and nonlinear part, right? So we will start with a decomposition, similar decomposition for the eigenfunction as well. Let's say h of x. So this is my linear part. Yes. Yes. A whole thing, yes. So, I mean, we haven't got to the Koopman yet. So all I'm saying is that given a nonlinear system, I can always write it this law. There is no eigenvalues will be part of the Koopman operator. Yes, but the eigenvalues of the linearization are also reflected in the eigenvalue of the Koopman. So they are not, I mean, the eigenfunctions may be still global. They are not like restricted to the point, but the eigenvalues information is retained in the eigenvalues of the Koopman. Okay? Because I think although it's a linearization at a point, but there is an equilibrium point. So that actually has like it dictates to bigger extent what the system behavior is, right? So that's why the information or eigenvalue is still retained in the Koopman, although it's global. Okay? Because imagine that you have a nonlinear system and you have a stable equilibrium point, right? And then the equilibrium point has all eigenvalues in the left half plane, right? So although it's only one point, but everything is kind of globally getting attracted to that point. So in that sense, that single point is actually of great significance. Okay, and hence that information, what is of the eigenvalue, is also reflected in the Koopman eigenfunctions. Okay. I think I forgot to tell you. Yeah, I think maybe one thing which I kind of forgot to mention when we talk about this Perron-Frobenius, like we never really discussed that. I mean, I didn't discuss that. Like one could ask, okay, just like we did the spectral analysis for the Koopman, what about the Perron-Frobenius? Right? Does the Perron-Frobenius also has a spectrum properties, or what does the spectrum of the Perron-Frobenius looks like? I think the answer to that is yes. I mean, the spectrum of Perron-Frobenius actually is very important, and people have been investigating that for quite some time. Maybe I can, let me finish this and I'll come back to it, because I think that the Perron-Frobenius operator, the eigenfunction of Perron-Frobenius operator carries actually very, something which is very physical, right? Like this kind of came when I talk about the equilibrium point. So if you have a system which is, the only problem with the spectrum of the Perron-Frobenius, which is a good thing about the Koopman and bad thing about Perron-Frobenius, is that the Perron-Frobenius spectrum is actually, could be very weird, in the sense that the spectrum may not be smooth. It could be a delta distribution. Okay, and I'll tell you more about that once we finish this. So anyway, so what we are trying to say here is that just like my system has a decomposition into linear part and nonlinear part, why don't I actually assume a decomposition of the eigenfunction also into linear part, nonlinear part? Okay, this is this doesn't mean that these eigenfunctions are only defined locally and so on, right? Because the definition of the eigenfunction is still sort of global. I mean, global in the sense is that this is a definition. So there is no, in this definition, there is no sort of restricted to a equilibrium point. Okay. So now if you do that, then what you do is you plug this in this formula, which is so you plug this expression in this, okay, and see what happens. So if you plug this, what do you get? So you get W transpose. So this partial phi lambda partial x is, think of that as a row matrix, right? Because it's a row matrix and F is a column. So this is the dot product. So you get a scalar. So left hand side is scalar, right hand side is scalar. So so for the linear part you get W transpose, and then for this one you get this times F equals lambda W transpose x plus H of x. So the H of x is purely nonlinear. What do you mean by purely nonlinear? It means that partial H, partial x at 0 is 0. There are no linear component there. Okay? Because all the linear components are here, just like and do a decomposition of the system. Now, if you equate this, now F also has a decomposition. So F partial H partial x, F also has decomposition Ax plus Fn of x plus lambda W transpose x plus H of x. Now, if you simplify this, what you see is that the linear part has to match with the linear part. That is W transpose Ax to be equal to lambda. Oops, this should be equal to lambda W transpose x. And then a nonlinear, the rest is all nonlinear. Ax plus Fn of x equals lambda H of x. Am I missing some terms? Yes, and yes, sorry, I'm missing a term. Plus W transpose Fn of x equals lambda H of x. Okay, so this is the linear part. This is the nonlinear part. Right? Now, what does this tells you? This has to be true for all x. So what does this tells you? True for all x. That means W transpose A equals lambda W transpose. Right? See, our goal is to actually find this. Our goal is to find what is W and what is H is, right? So as far as W is concerned, what does this tells you? W is nothing but the left eigenvector with eigenvalue lambda. Okay? W is nothing but the left eigenvector with eigenvalue lambda. So you see, the eigenfunction, so if you have a purely linear system, the eigenfunction of the Koopman operator for the linear system is given by W transpose x, where W is the left eigenvector with eigenvalue lambda. Okay. Now for the nonlinear part, you get this linear PDE. For the nonlinear part, you get this linear PDE, which is partial h, partial x times f of x. I'm just rewriting this again as f of x because that's what it is. Minus lambda h of x plus W transpose Fn of x equals 0. linear PDE. Now, let's say you have a system with a stable equilibrium point, okay, and it has some domain of attraction. Then one can show that these eigenfunctions are well defined within the domain of attraction. And these eigenfunctions, now there is how many eigen, so they have n eigenvalues, and you'll have n eigenfunctions. Now these eigenfunctions can be used, these are what we call as the principal eigenfunctions. These eigenfunctions now can be used as a change of coordinates to convert this nonlinear system to a linear system where the linearization is valid within the domain of attraction. So this is kind of actually linearization of a nonlinear system in large. And this is the change of coordinates coming from, can be related to the famous Hartman Grobman theorem. So while the Hartman Grobman theorem talks about there exists a change of coordinates which can convert a nonlinear system to a linear system locally in a neighborhood, what this tells you is that this change of coordinates is not local. This change of coordinates are true inside the domain of attraction, and this is a procedure to find this change of coordinates. Make sense? So the eigenfunction can be used as a change of coordinates. Eigenfunction associated with the principal eigenvalue, that is the eigenvalue which are the same as that of a linearization of nonlinear system. Make sense? Yes, good. So that's what I'm going to talk about now. Okay, good. That's a good question. So I'll tell you actually, so this is actually, because this is a linear PDE, one can actually write down the solution of this. And under some assumptions, we can also write it on an explicit solution, okay? So to answer your question, a stable manifold are given by looking at the zero level curve of the eigenfunction correspond to the unstable eigenvalues, okay? So if you're looking at stable eigenfunction, if you're looking at stable manifold, you look at the unstable eigenfunction, that is the eigenfunction associated with the positive eigenvalue. Look at a zero level curve. Zero level curve means the set of all points where these eigenfunctions are zero, like a joint zero level curve, right? And that zero level curve will constitute a stable manifold. On the other hand, if you're looking for unstable manifold, then look at the joint zero level curve of the eigenfunction corresponding to the stable eigenvalue. And that gives you an unstable manifold. So this is, I think, is quite powerful. And as I said right at the beginning, this hasn't been exploited. This is sort of fairly new. I'm going to have one paper on this, which if I get time, I'll talk about it. But you can now imagine actually applying this, especially in a data-driven setting. For like if there are plenty of applications where actually people are interested in knowing where the stable manifolds are, where the unstable manifolds are. Like one particular example is again ocean flows, oceanographic flows. Like this stable manifold, unstable manifold basically forms a skeleton, right? So if you think about it, they form a skeleton because these actually manifolds actually dictate where things actually move. Like these actually defines a partition in the state space. So if you're looking at oceanographic flow, people are interested in knowing where the contaminants, if you put some contaminant, let's say there is an oil spill in the ocean, and you want to know where the oil is going to, the spill is eventually going to get settled down. These are the manifolds which will kind of guide you. And computing this actually has been a hard problem, and it is still a hard problem. But this actually provides a very different way of actually looking at this computation of these manifolds from the eigenfunctions using data. Okay, so I'll tell you now how to actually now use data to actually even solve something like this, and we have used that in some of our research. So that's just one application. In fact, I'm just going to talk about this. I'm not. Those who are familiar, maybe you can see this. In fact, if you look at the optimal control problem, the optimal control problem of a nonlinear system can be the solution of the optimal control problem is given by Hamilton-Jacobi equation. Okay? Now, solving the Hamilton-Jacobi equation is like everybody wants to know how to solve the Hamilton-Jacobi equation because it has so many applications. Now, the solution of the Hamilton-Jacobi equation can be found using so-called Lagrangian submanifolds. So these are also unstable manifolds of a special system is called Hamiltonian system. I can actually write down this thing much more precisely and I can tell you, but the point I'm trying to make is that even the optimal solution or solution of the optimal control problem can be derived from a stable unstable manifold. So there's a way to actually use this methods or use this principal eigenfunction ideas to compute the optimal control without actually going through the model. So directly jump to the optimal control by computing the eigenfunction and the corresponding stable unstable manifold. So this is very powerful. I mean, the fact that now we can actually relate what is happening in the function space, especially the Koopman operator and its eigenfunction back to the state space, actually opens up a lot of things, okay? Especially with the presence of data. So coming back, and I'll write down that little more precisely what the statement which I just made in terms of stable manifold, unstable manifold. But before that, let me just say a few things about this linear PDE, right? So this is a linear PDE. Not only that, this linear PDE is actually derived from a ODE because x dot equal f of x. Everything is, and if you look at this, this is precisely the Koopman generator, right? This is precisely the Koopman generator. This with our notation is nothing but LF of h, right? This is the lead derivatives of the h along the vector field f. And the solution of this PDE can be written down implicitly. So what is the solution of this PDE? And for those who know anything about linear PDEs, there are various different ways of actually solving linear PDEs. One of the ways actually to solve it using so-called method of characteristics. And using the method of characteristics, you can actually write down the solution of this. So the solution of this h of x, I want to know the value of h at point x. It is given by e to the minus lambda t h st of x plus 0 to t e to the minus lambda tau w transpose fn st of s tau of x deta. So just take my words for this. This is actually the solution of the linear PDE using method of characteristics. This solution is not really useful because whenever you solve for PDEs, just like when you solve for ODEs, you need to know the initial condition. For PDEs, you need to know the boundary conditions, right? So that's why this quantity comes in. So this is not explicit because to know h of x, I need to know the value of h at st of x. And unless you know the boundary condition, this is not explicit. Okay? But under some assumptions, what you can say is that if you assume that system is stable, then you can actually get around this and you can write down an explicit form of this. So assuming that as t goes to infinity, if this quantity goes to 0, and that will happen under some assumptions which can be precisely characterized, and those are there in my paper, you can write down the precise solution of this. So I don't want to go into much more detail of this, but you can I can refer you to my paper, and I can also provide you with a code which you can actually use to compute this for some class of systems, which will actually help you to compute this change of coordinates, which can actually be used to linearize a nonlinear system in a large region, okay, not just in a small neighborhood. So these eigenfunctions can be computed, and those eigenfunctions can be used as a change of coordinates. Okay. Any questions? I think there's too much stuff in here. Maybe I'm just leaving you hanging at this point for those who will be more curious, and I could sort of entertain those questions related to like the applicability of the solutions and so on and so forth. The purpose here is actually to make you just aware of this, and if you want to look at some codes on this, I can make them available for you. Okay. So next I want to talk about is like write down this precisely the connection between the manifolds and the eigenfunctions. Okay. Any questions? So let's say you have this n eigenvalues, right? Lambda 1, lambda 2 to lambda n, right? And then you have the corresponding eigenfunctions, phi lambda 1 of x to phi lambda n of x. Okay. Oh, so yeah, so what is the st of x? Sorry, I think I'm maybe using notations which may are sort of confusing. So the st of x in this is actually the solution of that ODE, which I think we have been using some different notation. So let me change this notation so that it is more consistent. And I think what notation I'm using for the, yeah, so I'm using the phi. So this is s, instead of s, just call it as the phi t of x, with the phi t is the solution. Okay. And then we have this eigenvalue lambda 1, lambda 2 to lambda n. And then the associate eigenfunction, let me call this psi lambda 1 of x to psi lambda n of x, right? Okay, and so we're sort of assuming that the equilibrium point is hyperbolic. Now, what you could do is the following. So let's say I order these eigenvalues in such a way that psi lambda 1 of x dot psi lambda s of x, right? So these are the eigenfunctions correspond to the stable eigenvalue. Eigenfunction not stable. What I mean by stable is that these are the eigenfunction correspond to eigenvalue with negative real part, right? And then the eigenfunction correspond to eigenvalue with positive real part starts with lambda s plus 1 of x dot lambda n of x, right? So the first s eigenvalues are the eigenvalues correspond to the negative real part, and the remaining eigenfunctions are the eigenfunction correspond to the eigenvalue with positive real part. Okay, so this is sort of the partition one can do without loss of generality. And now you can ask, okay, what is a stable manifold? So MS is my stable manifold. What is a stable manifold? Stable manifold is set of all point x such that, now for stable manifold, I'll pick the unstable eigenvalues. I'll say phi lambda s plus 1 of x equals phi lambda s plus 2 of x dot equals phi lambda n of x equals 0. So this is basically the joint zero level curve. So these are set of all points where all these eigenfunctions are identically 0. Okay, of course this is a very small set, but that's what the stable manifolds are. Okay. And similarly, the unstable manifold will be exactly opposite. A set of all point x for which phi lambda 1 of x equals phi lambda 2 of x equals dot equals phi lambda s of x equals 0. Okay. And it's very easy to see. I mean, let's look at a simple example of a linear system and see how does this whole thing works out. Because we know for a linear system, how do you compute the eigenfunctions? Eigenfunctions for eigenvalue lambda, you just take the left eigenvector and then you just find it, right? So you see what happens. And it's quite of interesting. I mean, maybe you could do this exercise yourself and see. It makes sense? You don't do this linear system example to see how this actually works out, because in the linear system case, it's yeah, I'll need some help from you because I haven't worked out this example. So we'll have to be strategic in the sense that we have to cook up this example where I can write down this, I get a real eigenvalue so that I don't get into all this mess of this complex eigenvalues and so forth. By the way, I mean, these eigenvalues don't have to be real, okay? These eigenvalues could be complex, okay? This is not perhaps very clear, but these are all sort of assumed to be all complex here. I mean, these eigenfunctions are also complex. These are complex values eigenfunction. Of course, you can do a realifications and so on and so forth, but as far as this is concerned, there is nothing of real, not restricted to just real eigenvalues and eigenfunctions. Okay. So let's see if we can do this. So let's say if I have x dot equal to x, I want to actually, yes. So it's easy, right? So we have n eigenvalues, right? Let's say so let's say n equal to 3. So, and there are two eigenvalues which are maybe have a are in left half plane, one in the right half plane, right? So you find the eigenfunction corresponding to these two eigenvalues which are in left half plane. Those will be the stable eigenfunction. I mean, those will be stable eigenfunction, right? Which is in this notation will be this phi of s, right? And one eigenvalue is in the right half plane, so that there will be corresponding eigenfunction which will be phi of u, right? And now you take these two eigenfunctions and look at the set of all point x where these two eigenfunctions are 0. Both of them has to be identically 0, and that set will becomes your unstable manifold. And similarly for the stable one. So let's see if we can do with this simple example. So x dot equal to ax. What a you want to pick for which you know the eigenvectors and eigenvalues are real. And we can always pick the diagonal ones. It may not be fun. You want to pick the diagonal ones or to make life easy, or yeah, I mean, why not? So let's say 1, 0, 0, 2. Okay. What is the eigenfunction associated eigenvalue lambda? So eigenvalue minus 1. It will be W transpose X, right? So W in for eigenvalue minus 1 will be 1, 0, right? Left eigenvector. So it will be 1, 0. So it will be, yeah, so phi minus 1 of X will be simply X1, right? Make sense? Because this is W1 transpose X. W1 is just 1, 0, X1, X2. So this is just simply X1. Now what will be phi 2 of X? It will be W2 transpose X, which will be 0, 1, X1, X2, which is X2. Right? So the eigenfunction corresponding to minus 1 is X1, eigenfunction corresponding to plus 2 is X2. What is the definition of the stable manifold? So this phase portrait for this will be like this, right? So it will be minus 1. So this is going in this direction, and then this is going in this direction, right? So what is the stable and unstable subspaces here? So stable subspace is given by x2 equal to 0, right? So so what will be a stable subspace here? A set of all point x where phi 2 of x equals 0. But 2 here I mean like eigenvalue 2, okay, not that. So what is that? That will be x2 equals 0, right? That's exactly the stable direction, right? And what is the unstable subspace? It's set of all points where phi minus 1 of x equals 0, which is same as x1 equals 0. Okay. So of course this will work even if you do it a non-diagonal case, but just to make the point. Okay. Yes. N is the dimension of the system. So in this case, n is 2, the state space dimension. Yes. Yes. So here, you can also do it in that case. So you get what is called a generalized eigenfunctions. Like just like you have a like in the if the eigenvectors are not independent, right? I mean, it's so then you talk about this notion of generalized eigenvectors. Similarly, you can talk about generalized eigenfunctions. So then the same thing actually works. So this, yes, the same thing actually works. I mean, just the you have to write down a lot of things, but I mean the same thing works. Yeah. Yes. Yes. So because it's opposite, right? I mean, you see, it kind of makes intuitive sense too, right? If you're looking at a stable subspace, then you have to zero all the unstable thing. If you're looking at an unstable substance, then you have to zero all the stable ones, right? So that you don't have any contribution from that part, because then you sort of explode. Right? Yeah. I mean, you need little more technical. I mean, I have to I'm sort of ignoring them. You need to have like a, these are sort of inverse image. So you need a Jacobian to have a full rank and so on and so forth. But those are sort of differential geometry sort of assumptions one has to make for these manifolds to be smooth and things like that. Right? Yeah. Easy. You can cook this example very easily. So you instead of starting with the system, you started with the eigenfunctions, right? So let's say I pick some eigenfunctions, and then find a system for which those will be the eigenfunctions. So let's say I pick some eigenfunction. Let's say two-dimensional system. Say something like x1 plus x2 square. As long as this has to be invertible, right? I mean, you should be able to go back. Huh? X1, X2. I mean, I'm not sure if this will be like invertibles. Like if you define this to be the Z1, Z2, will be a like. So you have to find this properly. Okay, assume that. So you have to compute a Jacobian of this and make sure that Jacobian is non-singular, right? It may be non-singular for most x, but maybe some point x. So check that. So let me just, we can come back, we can change this thing once you find out that out. But now, what is this phi? Because this phi, and then pick the eigenvalues. Let's say I pick the eigenvalues. I want to make these eigenvalues to be, let's say, -1, -2. Okay? -1, -2. It's not, Jacobian is not all, but it says most of the point. Okay, that's fine. So let's say I want to pick these as my eigenvalues corresponding to the eigenfunction, right? Now find a system which will do this. What is that? So the way you do that is because I know that because these are eigenfunctions, then they should satisfy the following. I'm writing in a matrix form, right? Where phi is now a vector, lambda is now a matrix. Now what is this? Now this partial phi, partial x, because this is non-singular, I can write down f of x as partial phi, partial x, inverse lambda phi of x. So this is my dynamical system now. So for this system, phi will be the eigenfunction associated eigenvalue lambda. So you're just doing reverse engineering, right? Exactly. It's just a nonlinear change of coordinates. And you see, I mean, this equation is in a sense precisely the nonlinear change of coordinates, which happens to be the eigenfunction equation or the Koopman generator. And that's why I'm saying that this lot of things we do now in controls or in the system theory is very much tied to the Koopman. Is very much tied to the Koopman. But what is new now, or I mean, what is the novel thing is that now we can sort of do it from data. We can now like employ data to sort of realize a lot of these things. Mm-hmm. Yes, so this basically will provide you a, yes, so now basically what this, as I was saying, I mean, this now allows you to sort of compute this change of coordinates, maybe numerically. See, one of the challenge is the differential geometry. If that's where the question is coming from, with various tools in differential geometry, is that they are very elegant tools, but they don't support numerically. And that has to do with the geometric approach, right? All the geometry is very nice, but you cannot do computations with geometry. But now, because of this way of I'm looking at this more from a functional point of view, not from a geometric, more from a statistical point of view, it allows me to do computation. Right? So we can now actually do computation. So a lot of things we are, and I think that's a very interesting theme, which I think could be explored further, is that all the things that we have learned in differential geometry can now actually be, can we wrap a computation around that using some of these methods. Like the things like observability, controllability, all those notions can now be actually connected with this through this Koopman lenses.